excited state of scandium is what? We have these particular electronic configurations A, B, C, D, and you might be asking yourself which one is it? Now there are a couple of key steps that you need to remember for you to accomplish this. But before we look at the steps, let's look at the rules in terms of electronic configuration and filling out electrons based on the orbitals. And this here will allow us to make our life easy by eliminating right away the wrong answers here. And looking at all this here, you should highlight which one. You should highlight option B here. Says that we have 1s and we have 2s, but the 2s has 3 electrons. 3 electrons. That is not allowed. Absolutely. Every orbital must have maximum of 2 electrons, and there are some cases where there are some orbitals that have more than 1 orbitals. In this case, degenerate orbitals, like for example the 2p's, and those 2p's, they do have 3 of them. Each of them should have 2 electrons each for complete filling, and so right there we know automatically that B is a failure right away. And green tells us that yep, B is not the right answer because of this one right here, but other ones here, they are contenders. So let's dive into the next thing, which is, hey, let's locate our particular scandium on the periodic table. We see that scandium is located right around here, and looking at the 2 parts of your periodic table, the group here that it is in group 3, and the period is what? Period 4. And so when you're able to make that conclusion, you should be able to look at the next step, which is how many electrons do we have here for scandium in any state, in this case ground state. And so in here the number of electrons is equal to what? 21, and this here is pretty much found looking at the atomic number. And so once we have this highlighted, the next step is what? How are we going to count and also distribute the electrons in this particular orbitals? And this is where the easiest way is using your specific periodic table to address it. And for you to make that conclusion, the periodic table, that this particular section here is what? Your 1s. So once you have your 1s, next is your 2s, which is right here, and next is your 2p's right over here, 2p's. This here followed by your 3s, and then this here is your 3p's, and next is what? You have your 4s, which is right here, and the final part here is your D block, which is the 3D. And what we see is that yes, scandium is at the D block, which are the transition metals, and a lot of weird things happens when you're looking at transition metals based on the electrons, and some interesting movement or filling rules that may not apply to your regular rules in terms of filling of electrons. But for now, let's go with the regular rules here. So we said that we have electrons filling. In this case, we have the first one, which is our 1s2. We add our first 2 electrons, followed by the 2s2, and now we have 4 electrons. We add 6 electrons to the p orbital, and in this case, in total, we have 10 electrons that are filled out, and we have now in this case 11 left. And we have our 3s2, we have our 2 electrons in there, we have our 3p6, and this here is what we call the specific condensed form, where the core state here in here, which are the stable state, these here are known as the previous noble gas electronic configuration, which is known as, in this case, argon. And this argon here has this specific electronic configuration, and argon is around here. This is where its position is on the periodic table. So once we have this, we now have our how many electrons left. When we look at all this here, we've used up in total 18 electrons, and so we're going to subtract our 18 from 21, and we have 3 electrons left. And so these 3 electrons that are left, we have to distribute them using the rules in terms of energy level. That is, in this case, 4s is more stable and it is of a lower energy than that of the 3d. If you fill your 3d first before your 4s, those electrons are unstable, so they need to be in an energetically stable state. In this case, 4s has to be filled first, so our s orbital should have 2 electrons, so we're going to have our 4s2, and then that one last electron is going to be right there going to our 3d. And so once we have this, we have our ground state electronic configuration, which looks like this right here, where there's no energy that is put into that atom or energy going out of that atom. And so in this case here, this ground state electronic configuration, we need to use this to build our energy diagram of the ground state and what happens when it is going to the excited state. So this is how it looks like. And so now once we have this diagram, we have our 4s to be at a lower energy level, and then right above is our 3ds, and it's pretty much the same both on the ground state side and also the excited state. Now 3d, as you notice, have 5 degenerate orbitals, and these orbitals are of different orientation due to the magnetic quantum numbers, and that is something to keep in mind. And each of these orbitals that you see should have maximum of 2 electrons with a top spin and opposite spin, and these here are all pretty much what are the rules that you need to remember in terms of filling electrons. So first is for the ground state, we said that this electronic configuration here should be satisfied, and this here shows that we have our 4s 2 electrons, the top spin and the down spin, that is our 2 already done, and lastly is our 1 electron, which is going to be placed at the 3d, and this here is how it looks like at the ground state. Now when we are moving over to the excited state, excited means that you're getting that 1 electron from a lower energy to a higher energy. And so what happens is that to accomplish this, we need to put in energy that is going to be absorbed by this electron, and that energy must be discrete. That means it must be specific for it to go from that particular previous energy that it was to this energy right here, which is a 3d. And so what you see is that once that energy is gone into the electron, that electron jumps, and what happens is that your 4s now has 1 electron, and your 3d, which originally had 1 electron, will be joined by the 4s's second electron. And so what happens at the end is that we have this electron now at the 3d state. So in here we have our new electronic configuration at the excited state to be we have a condensed form, which is the AR, and we have our 4s 1, and we have our 3d 2. And so once we have this highlighted and stated, we're going to look at our options and look at which ones matches the ground state and which one is the excited state. So once you look at this, you see that in here we had our first 3d placed first and then 4s later. This here is a deception move, and the actual position should be the 4s's and then the 3d's. And so once we have that, now we can proceed by looking at which one here is the ground state. This looks like the ground state electronic configuration, and so automatically here A is wrong because this here represents the ground state. And so looking at our D, we notice that hey, the number of electrons seems to increase by 1, so that means this must have gained an electron to move into a state from a neutral atom to an anion. So this here should have a negative charge, so this is automatically a no configuration. And finally here is this particular C, which shows that we have our 4s1 now having that one electron that was there, which was at the ground state, to join the excited state, which is a 3d2 now, or 3d1. Now it becomes a 3d2. So this here satisfies our specific condition that we must have an excited state, because your electron has to move from the lowest energy level to the highest energy level. So overall, I hope you found this really informative in terms of how to address excited state of an atom, in this case scandium, and I hope you found this really informative. Please hit the comment down below, let me know your thoughts about other ways by which you can address this. If there's any faster way, please drop down into the comment section and let me know your thoughts about this. All the same, stay smart as always and keep on practicing.